In this lesson, we'll go over the equation of an ellipse. But to start with and explain where this thing comes from, let's look at this particular circle, a circle of radius 1 whose center is at the origin. One thing that you can find pretty easily from this equation are the x and the y intercepts. So for example, if you want the x-intercepts of this equation, which are here and here, you can see them on the graph itself, but you can also go to this equation. You can let y equal 0, and the equation becomes x squared plus 0 squared is equal to 1, or simply x squared is equal to 1. And by taking the square root of both sides of this equation, you get that x is equal to both plus and minus 1, which is no surprise. You get this point here and this point here. That came from setting y equal to 0. Likewise, if you want the y-intercepts from this equation, so if you want the y-intercepts, this time you could let x equal 0 in the equation. And when you do this, the equation becomes 0 squared plus y squared is equal to 1, or simply y squared is equal to 1. And by the same logic, if you take the square root of both sides, you get that y is equal to plus or minus 1. So it's easy to find these 4 points, not just from the graph, but from the equation itself. All that being said, what if we make a slight adjustment to this equation? So the equation is x squared plus y squared is equal to 1. Well, what happens if I, let's say, divide y squared by 4? This will no longer be the equation of the circle just because I have a new number under the y squared term. But what will this equation look like if you try to graph it? That is, what if we try to find the x and the y intercepts? Where will they be located? Let's start with the x-intercepts. If you want the x-intercepts on this new equation, you take the same approach. You would still let y is equal to 0, and you're going to solve for x. When you do that, you get that x squared plus 0 squared over 4 is equal to 1. That's the same thing as x squared is equal to 1. And by taking the square root of both sides, you get two solutions again. You get x is equal to plus or minus 1. So on this brand new equation, the x-intercepts actually did not change. They're still at -1 and +1. So I'm going to mark a point here and here. So that's on this new graph. Well, what about the y-intercepts? So what if you want the y-intercepts? So this time you're going to let x equal 0, and something different happens. This time you have that 0 squared plus y squared over 4 is equal to 1, or simply y squared over 4 is equal to 1. But this time, before taking the square root, you can multiply the 4 to the other side of the equation. And when you do that, you get y squared is equal to 4. Now, when you take the square root of both sides, you actually get a different number this time. You get that y is equal to plus or minus 2. So that is here and here. So this equation is very close to this one. It's still going to be kind of like a circle in some sense, but the fact that we divided the y squared term by 4 meant that it stretched out the y-intercepts. The equation that goes through these 4 points has this type of shape to it. So I'm going to try my best to sketch this on here, but we get this. Okay, this comes down like that. And this is a decent sketch of the new graph. So this is actually an equation of an ellipse. If you divide the x squared and y squared terms by numbers, and the two numbers are different, so like technically this is x squared over 1, what that will do is stretch a couple of the points while leaving the other 2 points the same, so your equation that you end up with is an ellipse. So to go from a circle to an ellipse, all you need to do is make sure the 2 numbers in the denominator here are different. And if you do, you get a shape that resembles something like this. To take a second look at this, again starting with this equation of the circle down here in red, what would happen if instead of dividing the y squared term by 4, we divide the x squared term by 4? Probably not a big surprise that, well, this time the y-intercepts are still going to be at 1 and -1. So that does not change. We still get a y-intercept here and a y-intercept here. However, if you try to find the x-intercepts, you're going to let y equal 0. And in the equation, you get x squared over 4 plus 0 squared is equal to 1, or x squared over 4 is equal to 1. When you solve this equation, x squared is equal to 4. Taking the square root of both sides will give you that x is equal to plus or minus 2. So now it is the x-intercepts that have moved instead of the y-intercepts. So if you sketch the equation that goes through it, all right, we get this thing, and that is an equation of an ellipse. Again, the same idea is holding true here, where if the numbers under the x squared and y squared terms are different, you don't get a perfect circle anymore. Parts of the graph are being stretched more than others. So this takes me to the standard form of the equation of the ellipse, and they can be written like this or like this. The difference between a circle and ellipse here is that in the denominators, we're going to put a term a squared and a term b squared. Perfect squares are nice because in terms of finding the intercepts, they'll be either at a or b. Here we're going to use the convention that a squared is greater than b squared. So with the examples that we just looked at, if the number under the x squared term is bigger than the one under the y squared term, that means it's going to stretch more in the x direction. Specifically, the x-intercept here and here are going to be at -a for x and +a for x. The reason for this is if you put 0 in place of y, it cancels this term, and when you solve for x, you'll get plus or minus a. Likewise, if you look for these 2 points, the y-intercepts, they are going to be at +b for y and -b for y. Maybe just a little terminology here. We call this longer axis the major axis. So if we go from here to here, this is the major axis, and we call this point a vertex, and this point a vertex as well. Now, how does this compare over to this equation where, well, what if the bigger term is under the y squared term instead of the x squared term? Same idea. What's going to happen is the points that are further away are going to be in the y direction this time. And the reason is, if you solve for the y-intercepts of this graph, x is going to be equal to 0, and when you solve for y, you're going to get plus or minus a. So in this picture, this is +a, and this is -a. And when you solve for the x-intercepts, that's going to come from this part of the graph. X will equal plus or minus b. So you get a +b here and a -b here. Now this time, the major axis is going in this direction. And then we call this a vertex and this a vertex as well. Another part of the ellipse that is very important is something called the foci. When we looked at the equation of a circle, it only had one important point, and that was the center. Now, technically, there is a center for an ellipse as well. For these both, they're at the point 0, 0. But there are a couple of other very important points here labeled in green, and we refer to these as the foci. They are used in defining the ellipse itself, but this spot here we'll say has an x-coordinate of -c, and this has an x-coordinate of +c. Same thing over here. We'll say the y-coordinate here is c, and the y-coordinate here is -c. There is a formula that will allow you to find these places on the ellipse, the foci, and that equation is the following. It is c squared is equal to a squared minus b squared. So here's the formula for it, and on the next slide, I'm going to talk a little bit more about what the foci actually represent on the equation itself. So here I have an ellipse, and it's stretched more in the x direction, and for this reason, the formula for it was, well, it's kind of like a circle. You know, it's x squared plus y squared is equal to 1, but you have to divide x squared and y squared by different numbers. We'll call the one under x squared a squared, and we'll call the one under y squared b squared. And here we're assuming that the number under the x term is greater than the number under the y term. That's why it stretches in this direction here. So just to recap, this spot here was at an x value of negative a, this was at positive a, this is b, this is negative b, and this spot here is at some negative x value, and this one is at some positive x value, which I'm calling c. And they satisfy the equation c squared is equal to a squared minus b squared. But what are these points and why are they important? Well, let's say you were standing inside a room that was in the shape of an ellipse, and you were standing at this spot here. And let's say you were to shine a beam of light towards the wall. When it reflects off, the spot that it first goes back to is this other spot here. And this is true no matter in which direction you shine a light. So if you were to shine the beam of light here, it would reflect off and go here. If you shine the beam here, it'll reflect off and go over here. So no matter where, it always bounces first back to this spot. Furthermore, these are the only 2 points that have this property. So like if you were to first, let's say, shine a beam of light from here, it might not go back to this spot. So it's these 2 spots that have this property. So that being said, this is the equation for the ellipse. This is a formula that you can use to find the location of these 2 points. So let's apply this in a couple of examples. Let's graph the ellipse given by this equation and then also locate the foci. For starters, if I look at this equation, I'm seeing the number under the x squared term is bigger than the one under the y squared term, so I know this is stretching in the x direction more than the y direction. I'll note that according to our formulas, we're saying that a squared is the bigger number, which is 36, and b squared is the smaller number, which is 25. I mean, this tells me that a is equal to 6, and that b is equal to 5. This makes graphing this particular ellipse pretty easy. The center is at 0, 0. To graph A, we're going to go 6 in both directions from 0, 0. So we get a spot here and a spot here. If you want to find the values of B, you start at the origin and go up 5 and down 5. So here and here. And that's really all you need. I mean, this thing is pretty close to a circle, but it's just stretched 1 unit more in the x direction. So I'll try to sketch that on here. So we get something that looks like this. Not a perfect sketch, but this is the idea. Kind of close to a circle, but it's off just a little bit because of this number here. If this number were also 36, you would actually have a perfect circle, a circle of radius 6, because you would have gone 6 in every direction from the center. All right, that being said, where are the foci? They have to be on this axis. They're always on the major axis of the given ellipse. And the formula that we have to solve for it is c squared is equal to a squared minus b squared. So c is equal to, well, a squared is 36, b squared is 25. And if we take the difference of those two numbers, that is 11. So if we solve for c itself is the square root of 11. Now this number in my calculator is approximately 3.32. So, 3.32. So if I'm actually trying to graph these 2 points, It's 3.32, so I want to put a spot about there. And then we get another one, right about there. Not perfect, but this is the exact value of C. This means the foci are located at negative the square root of 11, 0, and also positive the square root of 11, 0. So these are the foci. There are two of them, and they fall on the major axis, which is this x-axis. All right, let's work backwards in example 2. This time, I want to find the standard form for this ellipse, so go from the picture to the actual equation itself. First thing to point out is that, well, the major axis is in the y direction. So if we're assuming that our a squared is still greater than b squared, the equation would have to be x squared over b squared plus y squared over a squared is equal to 1. I'm putting the larger value under the y squared term because it's stretched farther in that direction. So the question is, well, what is A and what is B? Like, what are those two things? A is going to be the distance from here up to here, and that spot here is 8, so A is equal to 8. B is the distance from here to here, which appears to be 4. Now, on the equation, I want to square both of these numbers. We want to use a squared and we want to use b squared. So a squared is 64 and b squared is 16. Therefore, the equation is x squared over 16 plus y squared over 64 is equal to 1. To get the foci, I'll use this equation. C squared is equal to a squared minus b squared. And we know both a squared and b squared, that is 64 minus 16. So we get that c squared is equal to 48. Now we're going to take the square root of both sides of this equation, and the value that we get for c, the square root of 48 is not a perfect square, but I think we can reduce it a little bit. Let's see. I think 48 is divisible by 16. Okay, just a little work off to the side here. I'm thinking of how to reduce 48 under the square root. So 48 is equal to 16 times 3. So I'm really taking the square root of 16 times 3. This perfect square under a square root is nice because if you take the square root of 16, well, that just reduces down to 4. But the 3 is still under the square root, and technically this thing is a little bit more simplified. So this is my value of c. Now, where are the foci themselves? This time, the major axis is the y-axis, so one spot is going to be, well, where is 4 root 3? Let me type that in my calculator. 4 root 3 is about 6.93. So let's see, this is, this thing here is roughly 6.93. So one spot is up here, and there's another one down here. This means the actual coordinates, if I use an exact value for the foci, are 0, negative 4 root 3, and also 0, 4 root 3. There is a positive one and a negative one. Let's find the standard form for the ellipse with foci negative 3, 0, 3, 0, and vertices negative 12, 0, and 12, 0. So the x values are non-zero. That means it's stretching further along the x-axis. The equation must be of the form x squared over a squared plus y squared over b squared is equal to 1, again, where a squared is greater than b squared. Now, the vertices are at negative 12 and positive 12 for x. which is actually outside of the graph that I put on here. So I'll just kind of mark that, well, I know one of them is over here and the other is over here. Now these values are what A is equal to. So we already know that A is equal to 12, and therefore A squared is equal to 12 squared, which is 144. The other piece of information that we have is the location of the foci. So one is at +3, so there's one here and another one here. Okay, well, what does that mean about the location of B? Like, how far are we going in this direction and this direction? To figure that out, we're going to use the formula C squared is equal to A squared minus B squared. We're told that from the foci being 3 and -3, that's C. Therefore, C squared is equal to 9. So I'm going to put that number here. And we know A squared is 144. This will allow us to solve for B squared. I guess I'll subtract 144 from both sides of this equation, and I get -135 is equal to -b squared. And I can cancel the negative from both sides, and I get -135 is equal to b squared. We don't need this number, but if you want to know the value of b, we would take the square root of both sides, and the square root of 135 is about 11.62. So that's about 11.62. So that's off the window as well. There's a spot here and a spot here. We have everything that we need to plug into our equation. The equation is going to be x squared over a squared, which is 144, plus y squared over 135, that was b squared, is equal to 1. One thing to point out is the closer the two foci are together, the closer they're both to the point 0, 0, the closer your equation is a circle. So when I solve for b and -b, it's not a surprise that they're really far away. And the reason is, if these two foci actually met up here at the center, our equation would be a circle, and therefore it would go a distance of 12 in all directions. But that didn't happen, it was slightly off, and this is our equation. In this last example, we want to find the standard form of the ellipse from this graph here. And the center of this is no longer at 0, 0. I mean, it kind of looks like the center is here, so I'm going to go ahead and mark that. It appears that the center is at, it looks like -1, 1. It's not really marked on here, but we count over 1 and go up 1. Okay, so from here, I'm noticing that it is stretched more in the x direction than the y direction. So I know the equation is going to be of the form, x squared over a squared plus y squared over b squared is equal to 1, where a squared is greater than b squared. But the issue here is, just like with the circle, so like here I have just x's, and this will only work if your center is at 0, 0. What you can do if you want to shift this over to a center of -1, 1 is you do the following. It would be x minus the x value here, so x minus a -1 is really x plus 1 squared over a squared. And then we add on, okay, it's y minus this number, y minus 1 squared over b squared is equal to 1. To complete this equation, all we need to know is what is a and what is b. Now a, not a squared, but just a itself, is the distance from this center to this vertex here. Again, we're not counting by ones anymore, but here you're a distance of 1, a distance of 2, and now a distance of 3. So a is equal to 3. The hash marks are, really a half. Likewise, if you want to know the length of b, that's the distance from the center to this endpoint here. And this actual length is just 1. So I know b is equal to 1. Therefore, a squared is equal to 9. And, well, b squared is also equal to 1. So when I put this information into this equation, I won't even write a denominator over here. I'll just put divided by 9, and this will give us the equation that we want. Our equation is x plus 1 squared over 9 plus y minus 1 squared is equal to 1. It is this equation that gives us this graph. Now the next thing is, well, what are the foci? We can still use the same equation. It is still the case that c squared is equal to a squared minus b squared. That is still true. But when you solve for c is actually going to be the distance to the foci. So we have to be careful because, well, the center is no longer at 0, 0. So we just have to be a little bit careful with, what are the actual coordinates of it. First, to solve for c, let's see, c squared is equal to, well, a squared is 9 and b squared is 1. So, c squared is really equal to 8. And if you take the square root of both sides of this equation, you get that c is equal to plus or minus the square root of 8. 8 is equal to 4 times 2. You can reduce this square root. So this is really plus or minus 2 root 2. And since we're talking about a distance, here we can pretty much ignore that negative value and just take the positive. Now, 2 root 2 is not the actual coordinate for the foci. But what we can do is take this 2 root 2 and add it to this negative 1. So it'll move it from this point over here. And then you can subtract it from the negative 1, which moves it over here. So if you actually want the coordinates for the foci, you'll do negative 1, but then you'll add on 2 root 2 and put comma 1. So again, what this is doing is saying, go to this point, and to the x value, add 2 root 2 to it. Likewise, there's a second one. So you can do minus 1, that's the location of this coordinate, and subtract 2 root 2 from it. So I really want to just erase that, because what I'd like to do is subtract 2 root 2. So these are the foci. And that's for this problem.